All right, back from break. Let's flip the page over and let's see what we've got on this flip side. So we're going to start off with quantum states of electrons and hydrogen. So back chapter 39 kind of stuff. In fact, 1 and 2 look like they're both from chapter 39. In this case, we're looking at a 6D state in hydrogen. So I'm hoping those formulas are like super familiar. 6D state says that n is equal to 6. Oh look, L is equal to 2 again. We should have had this something different, but it's the same as on the reverse side. So putting those numbers in, putting in a 6 for the state number, ended up with minus 0.378 eV. So that's not much binding energy for the electron. Once the electron has excited all the way to state 6, it just takes a little bit of a nudge to have the electron ionize from that state. So a photon with not so much energy would be able to dislodge the electron if it's already somehow found its way into that fairly highly excited state, state 6. So that's easy enough. The angular, I hope, the angular momentum formula, we just plug in L is equal to 2. Here's the 2.45 h bars. Remember to leave your angular momentums in terms of h bars. Don't put them in kilograms, meters squared per second squared, whatever they are, meters squared per second. Just go ahead and leave them as h bar. H bar works out perfectly to think in terms of quantized angular momentum. Angular momentum is quantized in units of h bar. So that is much easier to think about. How many h bars do we have? Same deal as the other side, I guess, huh? Yeah, it is. So this is, now I drew this drawing, again, I don't think I was required to. It says list the possible values of L, LZ, and theta L, but then it does it for spin also. And so we did this for orbital angular momentum on that other example. We're getting the same numbers. I didn't do the equatorial stuff here, but I think that would be really handy to do. And then I did. Okay, this looks like I did get this done. I don't want to lose points leaving stuff out. It said identify all of the possible values for the quantum states, and there's 5 possible quantum states. Now sometimes students are unsure which quantum states are possible, you know, which ones go with which, and just write everything down thoroughly, and that's not, I mean, it's, stop and think of which states go with which. So if you're just writing a bunch, of quantum states down that really don't go together, that is not considered to be correct, okay? The idea here is to be able to identify specifically for a little l value of 2, which is what this problem says. It says it's a D state, little l is only 2, is nothing else. And if it's only 2 and nothing else, these are the only possible values m sub l could have. Okay. So moving on to spin, what I hoped we emphasized in lecture is that it's the very same formula, which means, see that square root sign there? I need a square root sign here too. How did I leave that out? Oh no! I got to get that put back in. So that needs a square root on it, for sure, but you guys picked up on that immediately, I know. So that's good. And then putting the numbers in, this is 0.866 h bar. And then same as before, this time I did do the equatorial approach. I drew the same angular momentum diagram, this time for spin, or intrinsic angular momentum. And here it's either spin up or spin down. And the m sub s values are plus 1 or plus a half or minus a half. The s of z values are 1/2 plus or minus 1/2 h bars in terms of units. These are the angles measured from the z-axis. Those are the equatorials. And again, you can see the equatorials are easier to think about. And you know, what's interesting, I guess, to me in this problem is that's not such a big angle. So the angular momentum is, it's fairly indeterminate in that we've got, let's see where the values are. This is 1/2, which is 0.500 in the z direction, but we have a total of 0.866. That's a fair amount. That's 0.366. Well, I guess we got to add them like Pythagorean's theorem. That leaves a lot of angular momentum to be divided up between x and z directions. Okay, so spin is, you know, fairly indeterminate. It's not like it's spin up and down, standing straight up or standing straight down. It's you know, it's at this angle, 35 degrees. All right, so I hope that was a good problem to start off on, something that was maybe not as difficult as some of the problems are. 2, I'm guessing, is going to be a little harder. 2 is asking about, look at that, it's the wave function for the 1s state all over again, only unlike on the other side, this time we explicitly wrote out what the normalization constant is for that state. Now we did that in class, we went through the derivation, how do you find out what the normalization constant, how do you evaluate what the normalization constant will be. And so it says here, show that the most probable value of r, the distance at which the electron is most likely to be found, is given by r is equal to the scaling factor a. So now we're assuming we know, well, I guess we're not really assuming we know the scaling factor. If we take this form of the wave function, we're assuming we know the wave function looks like. What we can do is square that. Okay, so I first of all have to square it. Now it's asking which r value is most likely. It's not asking what location is most likely. It's asking what r value. So it's not comparing one point with another. It's comparing one spherical shell with the other spherical shells. So if we divide this volume up into a series of spherical shells, so we're doing shell probabilities, how much probability here compared with somewhere else. So that requires that we take into account the surface area of that sphere. Okay, it's a volume effect. It's really the surface area times times dr. So what that gives us then is it gives us a function that looks like this. We've plugged in the wave function squared. And so I can take this wave function and the pi's are going to cancel out. What do we have? 4 over 8 cubed. Now it doesn't really matter what the constants are because we're looking to see, well, the graph is better. So here is the graph of that function. It rises and then it falls, and what we're trying to find out is what's the value of r at which the function levels out. So when we ask where does the function reach its maximum value, you guys know this from calculus, I hope you've done 1,000 of these problems in your calculus class. You take a function, you find out, you identify where the maximum point is by taking a derivative and finding out where the derivative goes to 0. Because that's where the function will level out, is where its derivative goes to 0. So we took the function, we took a derivative with respect to r, set it equal to 0, and then played around with the algebra and eventually showed that r is equal to a. So that's what they're looking for. Now, when I give this problem, and I've given this problem on exams more than one time, or something similar to it, asking where is the most probable value, for some reason, inexplicably, students integrate instead of taking a derivative. And I'm not sure why that is. So it's worth stopping and thinking about when they ask, well, let's read the problem, I guess. Find the most probable value of r for the electron. Show that it's at the location r is equal to a. So think, that's telling me if I do the probability distribution as a function of r, there's going to be a place where that function maximizes. To do that, I take a derivative and set it equal to 0. I'm not going to integrate. I'm going to take a derivative. All right. For some reason, students they lean towards setting up an integral rather than taking a derivative. And you've got to be ready to do either one, depending on what the problem is asking for. So we did part A. Part B says, all right, come back now. What fraction of the distribution is between r is equal to a and r is equal to 2a? Now we've seen, even in a problem like this that sounds relatively straightforward, the integrals can actually be pretty complicated. So here's the probability. I'm integrating values of r from r is equal to a to r is equal to 2a. There is the integration, same as what we set up before. And look at what function I'm trying to integrate. I am trying to integrate, tell me that's a 2. That's not, it looks like a 3. Oh my gosh. It's a 2, right? Because we squared it. So it's the same as the 2 here. Okay, block that out. So r squared, e to the minus, oh, there's a minus sign here too. Minus 2, oh, I see. That's the minus sign down below, and I squeezed the 2 in. So minus 2r over a dr. Now, what we've always done with these is we've used this substitution. What we've done is we've looked at the argument on the exponential, and whatever is there, we've called that u, or at least that's the symbol that I like to use. You can call it x or z or whatever you want. So I replaced that with u. Now u is unitless, and then I wrote down what r would be and what dr would be, substituted those in, and I have an integral that looks like this. Now notice in the problem that I showed that the results from, if I were to do this integral, I would solve it by using, by parts is the technique. So this would be integration by parts, and I would have to do that 2 times, and that would take too long for the midterm. And it's not a calculus class, it's a physics class. So I went ahead and just, wrote down a result. So that's what the integral is. Now I left off the constant value because when we're doing integrations, typically in physics, almost 99.9% of the time, we're putting in the limits of integration. Okay, that's almost always part of what's going on physically, is to put in limits of integration. And so we can take this expression and we get to use that. So on the problem, if it says, here's an integral that you may use, there's a good chance you would end up using it. Now, if by chance, so from time to time I'll see that students have integrated this on like a calculator. Because you can program a calculator to do this also. If you choose that method, let me know that you have programmed your calculator and solved the problem that way. But show your work. Don't have an answer that miraculously appears from nowhere, because you're not going to get full credit unless I can see the steps. I have to be able to see how you've approached the problem and how you've been able to solve the problem. So in any case, I did use that substitution. I put it in the form that I put it in terms of u, and it did appear the same way as this. So what I did was I used this formula they gave me. Now I used my trick of taking out the minus sign and reversing the limits. And I was able to find out what the limits are by putting in, let's see, if r is equal to a, u is equal to 2. If r is equal to 2a, u is equal to 4. So the limits of integration for u would be, not for u, but for the symbol u, would be 2 to 4. And remember, u is just unitless. It's just a number. And when I took a look at the variable substitution that we did, all of the scaling factors canceled out. Now that has to be true. So this is something also to watch for when you're carrying out a calculation. This is physics. The symbols all mean something. And that says, if I'm calculating a probability, I better have all the units cancel out, because probabilities don't have units. They're just numerical values. And so everything that had a unit in it went away. That's a good sign. Now, putting the numbers in for my probability, I got 0.439, and with kind of, with my understanding, I mean, I've been studying chapter 39, and I'm guessing that with your understanding of how these wave functions work, in particular the 1s wave function that we've worked with so much, you should be able to see that that's kind of a sensible number. And go, yeah, that would make sense. Between 1 and 2 could likely be 44% of the probability. All right. Let's move on. We're going to move on to, looks like we have a problem from, is that from 39 again? Oh my gosh, you know what happened here? There are no problems from chapter 40. So just, you know, to point that out, I don't think that's serious. There's plenty of other examples from chapter 40, but I did not get a chapter 40 problem put on this side. There's a couple on the other side that are really good problems to look at. So I'm going to move on here to problem 3. We're still in chapter 39. So we're looking at X-rays, which is a good topic to prepare for. X-rays, we said, can be produced if we're looking in materials that have, you know, medium-sized to large Z values. So even a couple of metals like copper or zinc, there is going to be enough energy separation between, I really wish we had an energy diagram here. I did not do an energy diagram. But if you go back and, we've done energy diagrams in other problems. So, you know, state 1, state 2, 3, 4, 5, 6, 7. I'm looking at state 2 and state 1. And what I'm finding for copper and for zinc is that if I use the Z-effective formulas, and Z-effective for these are equal to Z minus 1. So they tell us in the problem, copper is element 29, zinc is element 30. So the Z-effective for these energy transitions between state 2 and state 1 are going to be given by Z minus 1. That puts copper at 28 and zinc at 29. Now, the way we're calculating the photon energy is to solve this once for state 2 and once for state 1, putting in the Z-effective squared, and then for state 2, putting 2 squared in the denominator. That's the standard formula. And then 1 squared for the for state 1. When we solve that, that works out to be a factor of 3/4 coming from the 1 over 1 minus the 1 over 4 leaves us with 3/4. There's a factor of 13.6 common to both, and a factor of Z-effective common to both. So using that formula for copper, for element 29, I am finding the photon energies that would be produced specifically between state 2 and state 1. I'm predicting those at 7997 eV. Okay, so we're around 8,000 eV. And we said, you know, wow, that's a lot of energy. You know, in hydrogen, this was like, this transition from 2 to 1 was like 10 eV. And now it's 8,000 eV. So a huge difference. And for zinc, which is just one element beyond copper, that is all the way up to 8578 eV. Now it asks about the wavelength of the photon, and the wavelength is down in the picometer range. These are not nanometers, these are picometers. These are X-rays. So this is beyond ultraviolet. These are up in the thousands, you know, several thousand eV, and the wavelengths are down into picometers. Let's see. Okay, I got to go back and read the problem. Remind me. Okay, I'm sorry. The first part was copper and zinc, and this is actually the flip, the reverse question. It's saying, let's imagine we have an X-ray with wavelengths of 72 picometers. What element might that be? We have to do a comparison here. So the energy of this photon works out to be 17,200 eV. Well, that's much larger. So to create X-rays, really high energy photons, 17,200 eV, we must be well beyond zinc and copper. So we're looking at something, you know, significantly farther into the periodic table. So let's do this in reverse. The photon energy, we solved this formula once. We can now take the energy of the photon and solve for Z effective. So when I solved for Z effective, using that formula reversed, I got 41. That means that the element we're looking at is element 42, and that's molybdenum. All right. So good problem. Looking at the 2-to-1 transitions in medium size, not super heavy elements, but kind of medium size nuclei. All right, into problem 4, it says the following isotopes are among the most stable nuclei known. Which of these has the highest binding energy? Now it's really just asking you to solve for 3 binding energies. I'm hoping this feels pretty straightforward too. I'm guessing if you guys come afterwards, after the midterm, and say our midterm was harder than some of these problems, I'm going to say yes, it was. Some of these problems, 3 should be pretty straightforward, 4 should be pretty straightforward, 2 is a little more challenging here, 1 is kind of medium, 5 is kind of medium to medium difficult. Anyway, so let's go ahead and do this one. We've got in the problem, they've given us the masses of the proton, neutron, and electron. This time not quite as many significant figures. Just 6 places past the decimal is the level of precision, because we are going to be adding and subtracting these numbers. So for this, we do want to line up columns of numbers. So it's not like multiplying and dividing where it's the the number of meaningful digits that's important. So if we're going to keep calculations, again, addition and subtraction, accurate to 6 places past the decimal, everything needs to be out to that level. Okay, so just it's worth thinking about a little differently in terms of how many significant figures are we going to keep. And so if we, okay, and the solution is this. We're referring back, so these are the masses that you're given for the completed atom. So that's for the completed neutral atom, and we're going to compare those with the total added mass of neutrons, protons, and electrons. And yes, to get these numbers correct, you got to keep all of the digits that were provided. If you round back, you'll miss out on significant figures. Now on these, let's see, how important is that? We do have digits right from the start here. So our first 3 significant digits in this answer, for example, 0.517 atomic mass units. So these are big enough atoms that we're getting significant amounts of missing mass. But still, you got to have those 3 or 4 in order to get the answers. And we're keeping 4 significant figures in the answers. All right, so we add all these together, which we've done, and we subtract this off. For the iron, we add all these together and subtract this off. For the cobalt, so what this means is that if I'm being asked binding energies, and we had a problem on the flip side also asking about binding energies, you have to be able to count protons, neutrons, and electrons in a neutral atom. You have to, these would be provided, masses for protons, neutrons, and electrons would be provided. You have to make sure that you get all the digits included, add those up, add and subtract as needed. I guess in this case it's only addition that we're doing to get these numbers, and then we have to subtract these off. And so, yeah. And then we've got to get these using the 931.5 conversion. We've got to get these converted into MeV, and then get binding energies per nucleon. So, often during the exam, students will come up and say, do I have to do the total nuclear binding energy or the highest binding energy per nucleon, or energy per nucleon? And I always suggest just do both, just for completeness. And sometimes faster than asking the question is go ahead and just do the calculation, and then you're done. And it may actually look like you're being more thorough and understand things. So just do both, and that's what we've done here. This one specifically did ask for the binding energy per nucleon. And so this is where we would actually start to make comparisons. And the highest value we have here, the 8.790, came in with iron 56. Okay, so that's, you know, a little more stable. Another thing we talked about is that the binding energies are going to, the highest binding energies are 8 point something. There are no nuclear binding energies of 9 or higher unless we're creating a kind of an artificial problem with some element that we've made up, which I'm not sure how we would do that since pretty much all the elements are accounted for. It's not like we're missing any of those. So that's it. And so we're finding, for, at least among these three isotopes, the iron is the highest one. And we just have problem 5, so let's look at that. I think we're going to wrap things up maybe a little earlier than we could imagine. So the other flip side was overall, I think, more involved. But let's see what this last problem looks like. Because there's A, B, C, D, and look, there's even extra credit. So it's looking at radioactive decay again. Does it ask about binding energies? It does. So alpha decay to thorium. And so this is what that reaction would look like. This is uranium-238 isotope in particular, and that would alpha decay to thorium. Now in class, I've been writing the alpha particle as helium-4, a high-energy helium-4 nucleus coming out. So it's an alpha particle. You should know it's an alpha particle, but I think it's worth thinking about it as a helium-4 nucleus. It's basically what it is, one moving really fast. So it asks about binding energy of each side, the uranium and the thorium, and I'm following that same procedure, counting all the protons, electrons, and neutrons, and if I miss an electron or neutron, it will show up. So watch your results and see if they make sense. The uranium's coming in, and see, this is not the binding energy we saw in these guys. These guys were up, 8.7 or 8.8, something like that. These elements now towards the end of the periodic table have dropped down to 7.5. Okay, and so these radioactively decay into more and more stable, and you can see the uranium decaying into thorium, the overall binding energy per nucleon's gone up. So the thorium, in some senses, the thorium is more stable than the uranium is, okay, in terms of binding energy. Even though the thorium, remember, everything is radioactive beyond lead and bismuth. And so beyond elements 82 and 83, everything's radioactive. This is not going to last long. This thorium will also be decaying. Okay, and by last long, I guess the uranium-238 has a half-life of like 4.5 billion years. That's quite a while. But this is going to continue to decay through several elements until it gets something that doesn't decay. The Q value for this reaction, now this is easier. It's an alpha decay, it's not a beta decay. And so we can take the uranium, the thorium, and the helium. Remember, we want to charge balance. Okay, and so the reason that I'm writing this as a helium-4 coming out is to correctly count the electrons. When I look up these masses in Appendix F, which is your friend, by the way, Appendix F is going to have masses of neutral atoms. And if I use neutral atoms consistently, it will take care of the electron counting for me. That's our strategy. And so I do want to get the mass of helium-4 here. And taking these masses and subtracting off the thorium and the helium, I ended up with this much missing mass. That would be the Q value. That would be the amount of mass being converted to kinetic energy in this particular radioactive decay. Now, we had done formulas back in relativity that looked like this. And yeah, I do like these formulas. It allows us, they were in a couple of the homework problems too. So they showed up in the homework problems as just kind of standalones where you were supposed to start from scratch and conserve energy and conserve momentum and derive formulas for these decays. What we did instead is back when we did relativity a long time ago, right? Weeks and weeks and many, many weeks ago. What we did was we derived some of these formulas and then we keep bringing them back. I keep bringing them back because to remind you guys that we've already solved this problem and we've derived some formulas that we can use, and you can put these on your notes, it's fine. So the kinetic energies that we would have for a decay like this comes from just putting in all the masses. So if we identify m naught as the starting mass, that would be the mass of the uranium, and then the thorium and helium are going to be mass 1 and mass 2, and those can be put in either order. Then we can go in and solve. I guess I said atom 1 is the helium and atom 2 is the thorium. Then we can use the formulas that we've solved. We know the Q value. It's telling us now that the helium, the alpha particle, is going to pick up 98%, a little over 98% of the available energy. And that's a consistent theme that we've seen throughout ever since we've been looking at these these types of reactions, is that the lighter object ends up with more kinetic energy. And the reason being that when we have a two-particle decay, when we have something that's sitting there and then it breaks into two pieces and they head away from each other, each object starts out, well, each object has the same amount of momentum. And so we conserve momentum, and then once we conserve momentum, we find what that means is more kinetic energy for the lighter particle. So momentum, if we were calculating that, which it doesn't show here, would be identical for both of these. And that's saying that more than 98% of the available energy being released is going to the lighter object. It's going to the alpha particle. And there's a small margin here of how much energy is released, and that tends to create an even more dramatic effect. So less than 2% is staying with the thorium. There's a big difference in their masses here, and there's not that much of a Q margin to work with. Let's see, so that says, carrying out the calculations, the actual numbers, 4.209 MeV goes with the helium, and 0.0720 MeV goes with the thorium. Now, this is one of those situations, which is, I guess, every situation, most situations in science. There's always a, well, let's think more carefully about this. Is this using this mass for the alpha particle, is that accurate? And it's not, because the alpha particle doesn't take the electrons with it. The alpha particle is heading out at an incredibly high speed. It is not going to be able to grab onto two electrons. The alpha particle is just out of there. Now, notice the thorium also, if this is not anchored into some crystal structure, we're going to have the thorium also that's going to be heading out at some really high speed. And so some electrons could get left behind. Now, we don't know in any particular reaction how many electrons might be left behind. So what we're going to say is, we know that there's a built-in approximation here, but it's a really good approximation, and it's a pretty straightforward way to balance our equations and then get Q values and kinetic energies that are pretty reliable. They're going to be pretty reliable to work from. So that's what we're doing. We're using those formulas we've derived. Now in part D, was this the extra credit? It is, find the velocities. So this is actually, some more formulas we developed in special relativity. And, we learned those with the specific intent that we could bring them along and use them whenever we needed to. We used them when we develop some of the formulas for in chapter 38, I guess. In chapter 37 with with Compton scattering. So we've used these, and now in chapter 41 we're using them again. So for the helium, what I can do is I can take mu is equal to 1 plus kinetic energy over mc squared. Now this is a little tricky, so we got to ask ourselves, what is mc squared for helium? Well, the kinetic energy is given in MeV. So I want to get mc squared also in MeV. So what we want to do is start with, the helium has a mass of 4 atomic mass units, and now, you know, in chapter 41 we're routinely using a conversion between atomic mass units and MeV. So helium has 4 atomic mass units. I'm going to take that 4, multiply by 931.5. So write that in. This is 4 times 931.5. I know I should have added one more step in here, but that's what that mass will be. Now the kinetic energy here, or the gamma value, sorry, is 1.00113. So you're thinking, well, it's not going super fast. That gamma value is not too significantly different from 1, but when we go in and plug in our formulas from relativity, we find that even that gamma value, hey, this thing's going at 5% of C, so it's getting, you know, kind of borderline whether we would want to use classical physics, which would give us a slightly less reliable value for this. So, you know, probably using relativity here is worth it. We got something that we're figuring to 3 significant figures. It's going to be very reliable because, look, it's getting up 5% of the speed of light. Now, the thorium's a lot heavier. And the thorium is not getting nearly as much kinetic energy in this reaction. So the mc squared, what would the mc squared be for the thorium? What should I put there? So I have to think of how many atomic mass units the thorium would be, and then multiply by our conversion factor of 931.5. So instead of the helium, which was at 4 atomic mass units, the thorium is at 234. So I got to put 234 in there. That's like 50 times larger than or more, right, than what we had before. And so this is going to be 234 in the denominator, 234 atomic mass units times 931.5 MeV to put it in MeV and have the units cancel. This time my gamma factor, 1.00000033, that's sounding kind of low. It's not very different from 1. Now it was different enough that I was able to put this into my calculator and come up with this value, 0.000812 C. So we're down to less than 1,000th of the speed of light. And at that speed, I could go ahead and use classical formulas. Okay. In fact, at those speeds, you start to run a bit of a risk. If I have a gamma value here, that's almost 1. See, I've only got those 2 sig figs over here that are telling me how different. They could get lost in squaring and inverting, and so I have to be careful that at some point things could drop out of my calculator, and so I may want to go to classical formulas. Now the classical formula for this, one approach would be 1/2 mc squared times v over c squared. And so where the v over c is 2k over mc squared. So I can continue using the formulas, or the shortcuts. I can continue using mc squared, and I can continue using kinetic energy in terms of MeV. When I did that formula, I ended up with the very same value, 0.000812 too. So the classical approach, which you could, I'll say, for the classical approach, you could just go back and do everything in standard units. That would work. And at the end, take the joules and convert those back into MeV. That totally works if that's what you're more comfortable with. But what I did find is that the classical formula approach and the relativity formula gave me the same answer to, I'm going to say the significant, well, 3 significant figures. And so, yeah, either approach would have worked fine for the thorium. All right, so that's alpha decay. We've looked at some beta decay. We looked at binding energies from chapter 41. In chapter 40, we looked at diatomic rotational states, vibrational states. We looked at quantum states, kinetic energy, quantum states of electrons in a block of a metal. And then in 39, we've looked a lot at the hydrogen 1s state. We did some probability calculations. We took a derivative of the probability function to find out where the peak was. So it's a good, and we did the X-ray calculations too, and looked at quantum numbers. So it's a pretty good set of topics that we can work from that you want to be clear on. And then in addition to these, of course, be looking at homework problems and be looking at examples from class. So whatever, whatever you have time for. I know you guys have other classes also going on at the same time, but as much time as you can allocate to physics, that's a good idea. The midterm is not that far off. Don't wait until the night before. If you guys have questions at all, stop by office hours and we'll take a look at those.